You know how sometimes you forget where you put your glasses? And they're right on your head. Now imagine Earth doing something similar, but with 1 billion years. How does a planet misplace 1 billion years? What untold stories lie beneath the surface, where rocks speak and centuries vanish? Let's dive deep beneath the Earth's surface, where time plays hide and seek and rocks hold ancient secrets. Buckle up. We're about to rock the foundations of time itself. Ever think about how cool it is that our planet has a secret history? Meet the Great Unconformity. A mysterious time gap in Earth's resume. 1 billion-year-long lunch break, if you will. A curious case of lost time we're all still trying to figure out. How could this have happened? One theory points to change in sea levels. Think of global sea levels dropping so drastically that massive areas of land are left exposed to the elements. This happened during Earth's snowball phase and could have led to intense erosion, wiping away eons of geological history. Then there's the drama of supercontinents. Imagine continents coming together and breaking apart, causing global upheavals, sort of like Earth's very own soap opera. This could have affected everything, from the Earth's crust and mantle to the climate on Earth's surface, which in turn led to regional glaciations and erosions contributing to this lost time. And let's not forget about local factors. The geology and geography of specific regions, the presence of mountains, volcanic activity, and more could have influenced the formation of the Great Unconformity. The intriguing part? The Great Unconformity isn't just one event or one surface. We're still trying to piece together this grand puzzle, deciphering the stories that each rock has to tell, and have made some shocking revelations. We will unveil the truth later. But first, let's find out what the geologists uncovered. It's time to set sail for Scotland, where geological wonder awaits: Hutton's Unconformity. Picture this: Scotland, 18th century. James Hutton, a true Sherlock Holmes of geology, is piecing together Earth's deep history. His magnifying glass? Rock layers. Hutton spots something intriguing: older rocks and younger rocks chilling together with no layers in between. It's an unconformity, a mysterious gap in the geological record. He classifies them into 3 types. Firstly, we have angular unconformity. Think of it as an ancient rock rebellion. The old rocks got tilted or folded, then new horizontal layers cozied up on top. Then we have nonconformity. Here, ancient igneous or metamorphic rocks are topped by newer sedimentary ones. And thirdly, the disconformity, a subtle spy. Both the old and new rocks are sedimentary, but there's a secretive gap. Hutton's unconformity is an angular unconformity. At Sicker Point, he sees near-vertical gray Silurian rocks from a time so old it whispers tales of primordial oceans. Then, laid back atop are younger reddish rocks, remnants of Devonian rivers and Carboniferous deltas. Hold on to your compasses, because the gap between these rock layers accounts for a staggering 80 million years. This was game-changing. Back then, Earth's history was viewed through the lens of religious texts. But Hutton challenged this. He advocated for uniformitarianism, the idea that Earth's features are shaped by continuous natural processes. Not only that, but he also supports Plutonism, which argues that rocks form mainly from volcanic activity, not just from oceans. Hutton's discovery was a true paradigm shift. Sicker Point becomes a geological landmark, and Hutton? He's hailed as the father of modern geology. Now, let's voyage across the Atlantic and deep into the heart of the Grand Canyon in Arizona, where yet another geological wonder awaits: Powell's Unconformity. In 1869, American explorer and geologist John Wesley Powell navigated the Colorado River, a journey that brought him face to face with an extraordinary geological marvel in the Grand Canyon, Arizona. In the middle of the rugged landscape, Powell made a startling observation. A layer of flat-lying Cambrian sandstone covered a bed of tilted and eroded Precambrian metamorphic and igneous rocks. Powell's Unconformity, a nonconformity, showcases a 1.2 billion year history. The Precambrian rocks had undergone significant transformation: deformation, metamorphosis, intrusion by magma, uplift, erosion, and finally burial by Cambrian sediments. Interestingly, this discovery was initially made by John Newberry during the Ives expedition of 1857 to 1858 in New Mexico, 12 years before Powell's expedition. Still, it was Powell who named it and detailed its characteristics. He acknowledged the crucial significance of this unconformity, emphasizing that it represents a time interval extensive enough for mountains to form from sediments derived from an earlier land surface. Now, let's rewind a bit and dive into something that's just as gripping as Powell's unconformity. We're talking about the snowball Earth hypothesis. This theory has it that our blue planet wasn't always so blue. It was more like an icy billiard ball, at least once, maybe even a few times, way back in the day. Now, when exactly was Earth doing its impersonation of a giant snow cone? We're looking at over 650 million years ago, during what the geology buffs call the Cryogenium period. What's the scoop on this? Well, there's a bunch of clues that got the scientists thinking. For starters, there are these glacial deposits found hanging out where you'd expect palm trees, not icebergs. Then there are these iron-rich rocks that whisper of a time when the oceans were kinda low on oxygen. And let's not forget the carbon isotope anomalies that hint at some serious drama in the carbon cycle. So what got Earth to hit the deep freeze button? That's the million-dollar question. One thought is that the sun wasn't quite its bright and shiny self back then, about 6% dimmer actually. This could have set off this whole snowball effect where more ice reflects more sunlight, which cools things down even more. Then there's the theory that it's all about location, 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 of the continents that is. How they were hanging out might have changed the game in terms of ocean currents, rock weathering, and all that jazz. Some even think that a supercontinent closing up to the equator might have messed with the ocean currents enough to trigger this planetary popsicle event. And of course, we can't leave out the volcanoes. Depending on what they were spewing out, they could have either thrown shade at the sun with dust and aerosols or cranked up the thermostat with carbon dioxide. Now, turning into a snow globe probably wasn't the best thing for anyone living back then. We're talking possible mass extinctions, especially for those critters who were fans of sunlight and warm waters. But life finds a way, right? There could have been little hideouts like hot springs or pockets of water under the ice where life hunkered down and weathered the storm. And when things finally warmed up, life might have gone into overdrive, evolving like crazy. But hold up, not everyone's on board with the snowball Earth idea. There's a camp that thinks it was more like a slush ball Earth with a belt of open water around the equator. Others say it was more of a regional thing, no global VIP pass for the ice. And some reckon there was a mix of scorching and freezing going on, courtesy of those volcanoes and their carbon dioxide antics. Now, let's pause for a second and entertain this thought. What if the icy embrace of the snowball Earth had something to do with Powell's great unconformity? That's an idea that some scientists have tossed around. It's a possibility that these glaciers in their relentless march shaved off kilometers of rock around 720 to 635 million years ago. If you think about it, that kind of erosion can explain some of the missing chapters in Earth's geological book that we see in the Great Unconformity. And let's not forget those wanderer rocks or erratics found way down in tropical latitudes. Those could be the postcards the glaciers left behind. But hold on a second. Not everyone's sold on this connection. Some scientists think that we're looking at more of a local affair. They reckon that what happened in one area wasn't necessarily because of some big global event. Maybe it was more about what was in the neighborhood, like mountain ranges, volcanoes, or even early life mucking about. Now, there are also those who think the supercontinents like Rodinia were the puppet masters behind the Great Unconformity. Think of Earth's crust doing the tectonic tango, coming together and breaking apart over millions of years. That sort of movement could get things pretty heated and really change up the land, the oceans, and the weather. And who's to say that these dramatic changes didn't have a hand in the erosion we see in the Great Unconformity? Then there's the idea that maybe we're not just looking at one big unconformity, but a bunch of them stitched together. A geological quilt, if you will. Some experts think that most of the erosion happened either before or after Earth decided to play snowball, which throws a wrench in the whole snowball Earth caused the Great Unconformity idea. So where does that leave us? As we dig through the layers, who knows what secrets we'll uncover next?